matrix is m minus 1. See, because we have 0 in the first component. So for the incoherent noise component, we have a rank of m minus 1. And what is nice is that these three components are mutually uncorrelated. So each one is uncorrelated to the other one. So we can work, so we have summation also after taking the correlation between them. So we don't have cross terms, correlation between them, because they cancel out. So if we define the input signal to noise ratio, what will be the input signal to noise ratio? Using this model, what is the input signal to noise ratio? This is the variance of the desired signal. See? In all the components. So what will be the variance? What will be the power of the desired signal? The input, for the input SNR. What is the input SNR? How is it defined? For multi-channel. See? So what we need, the input SNR for frequency F. So it's the narrow band input SNR. How is it defined? The SNR in the reference sensor. Okay? So it's phi x1 F divided by phi V1 F. Okay? So if you see here, this is the correlation, the variance of all components. So actually, in this matrix, if you take the first element will always be 1. Okay? And then you multiply with phi x1. So this is the power of the desired signal, the variance of the desired signal, and this is the variance of the noise. The first element in this matrix, the top left element, is 1. Okay, because it's always the correlation between V1 and V1, it's normalized by V1, so it's 1. It's always 1. And here it's 0. Okay, so this input SNR will be phi x1 divided by phi V1. But also, if you take, you always, input SNR is compared to the reference sensor. So we know that it looks like that. The output SNR we need to define. How do we obtain? So if we obtain it using a filter, we need to write it as the sum of the desired signal plus noise. And then we can check what is the variance, so we will get the output SNR. So linear filtering is just like I wrote over there. Okay, so by the way, this filter is for each frequency. Okay, so I need to add here F. Okay, because we work on each frequency separately. So the filter for each frequency is a vector of length m, for each frequency. It's not the same filter for all frequencies, of course. That's why it depends on the frequency. So we can write for linear filtering, we say linear filtering, the output of x1, an estimate of x1f, is a superposition of the noisy measurement. So it looks like this, where this vector is defined as the gains that we give to each measurement in each sensor. So it's a vector of length m. Now I can write it, because I know that y, let's write it with the lowercase letter, so it will look like this, okay? So it's a vector like this. So I can write this as a summation of the component. Okay, the block diagram, it looks like that. So x1 plus v1 equals to y1. And then this is the gain that we give to the reference sensor. And this is the gain that we give to any sensor, okay, or to all sensors. So here we have the gains. We take the summation, we get an estimate of x1, f. Okay? So this is the block diagram of the model, summation, and also the gains in the frequency domain. So we have here that the estimate of x1 is h conjugate transpose multiplied with y, and we write y like this. So we have two components. One component is the filter desired, and one component is the residual noise. The filter desired is x1 f multiplied with h conjugate transpose steering vector or coherence function between x and x1, complex conjugate. Why did I move x1 to here? Because it's a scalar. Okay, so I can move scalar to anywhere where I want. So this is the scalar x1, and this is the vector, row vector multiplied with a column vector. So this is also a scalar. Okay, and this is all this is scalar, but this is a vector and this is a vector. And the residual noise at the output of the filter is H complex transpose, apply H complex transpose, multiplied with V, with the noise that is measured. So this is the residual noise. So if I ask you what is the output SNR, output SNR is the variance of X filter desired divided by the variance of residual noise. Okay, so the output SNR, narrowband, the narrowband output SNR will be the variance of X filter desired divided by the variance of the residual noise. Okay? So if I want to write the narrowband output SNR as a function of the filter, you see? So I can write it as phi x1 f multiplied with this number, magnitude squared. So it will be H complex or conjugate transpose multiplied with coherence function between x1 and x, magnitude squared. See, this is the variance of this part. This is something that is not random. That's why I take this value. The only random here is x1. So I take its variance divided by what? Expectation of this magnitude squared. Okay? So expectation of this magnitude squared will be expectation of H VF. Instead of magnitude squared, I write it exactly. Okay? So I'll take it as V okay? Like this. So this, I can write it as HF RV HF. Okay? You see? Or, sorry, instead of R, because we work in the frequency domain. So instead of R, we call it phi, okay? Because the correlation matrix in the frequency domain, we call it phi, okay? To make distinction between time domain and frequency domain. So it's a matrix phi V F, okay? This is the correlation matrix, like this. This is the variance of the residual noise at the output of the filter. And this is the variance of the filter desired at the output of the filter. So this ratio will give us the narrowband output SNR. Now suppose that I want to get filter with no distortion, like MVDR. So what should I require? So let's see what I have here. Okay, I go back. Here. You see, the output of the filter, we have two components. So this component, filter desired. See here, filter desired? If I want no distortion, like MVDR filter. So the filter desired should be what? X1, exactly. So X1. So the constraint or the requirement for MVDR, what will it be? Exactly. Okay. So we will require for MVDR, we will require the H, that H multiplied with gamma coherence function between X1 and X. We will require that this will be 1 for all frequencies. If it's 1 for all frequencies, what do we get? MVDR filter. So this will be the constraint when we derive the MVDR filter. If it's not satisfied, necessarily we will have some distortion. Okay? Questions? Continue. Okay, let's continue. So now we started already with the performance measures, but we can continue. Okay, so with the performance measure. So we have the narrowband signal to noise ratio, just like we wrote before. And we can define the broadband input SNR, which is the summation or integral of the variance over all frequency. So this is the power of the desired signal, the total power over all frequency. This is the total power of the noise, the variance of the noise over all frequency. So this is the broadband input SNR. And you see that the input SNR is not an integral of the narrowband input SNR, of course. We have also the output SNR. The narrowband output SNR is the variance of the narrowband power of the desired signal at the output of the filter divided by the narrowband variance of the residual noise at the output of the filter. So this ratio, we had it before. You see, it looks like this. Now question. If we have MVDR, what will be the output, the gain in SNR? So if we have MVDR, okay. So if we have MVDR, we have this, which is the same. You see D, the steering vector, is this steering vector. So here, the output SNR for MVDR we can write it the narrowband output SNR for MVDR will be phi x1 divided by H phi V H, okay? So if I take the gain in an SNR, the narrowband gain, which is the output SNR, the output narrowband SNR divided by the input narrowband input SNR, so it will be this divided by phi x and phi1. So we can write it as H F gamma V H minus 1, where gamma is the normalized correlation matrix. Okay, so gamma V will be the normalized matrix, correlation matrix of the noise. Okay? Okay? So, of course, with MVDR is the put no distortion, so the amount of gain in SNR is limited. If you want to increase the output SNR beyond that, you will introduce some distortion. Because MVDR, it says, don't touch the signal subspace. We remove the noise only from components or frequencies that contain no signal. So the gain in SNR is limited. But this is the gain in SNR that we can obtain using the MVDR. And also you can compute it for this is for the narrowband, you can compute it also for the broadband when we reach the MVDR. Okay, so the broadband output SNR is the integral of the total power of desired signal in the output filter divided by the total power of the noise, the residual noise in the output filter. And of course, also for the output SNR, the broadband, we don't have that it's an integral of the narrowband output SNR. It's different. Okay, so this is what it's possible to show. Okay, this is what I discussed. Okay, so the output SNR is smaller than a certain value like this. If I want to discuss it, I can skip that because I just wanted to say that using the MVDR, it's the least amount of output SNR. So usually you can get higher output SNR if you introduce more noise. So this is the output SNR that is obtained using the MVDR, and then we can continue. Or if we take a filter like this, of course, filter like this, it means that we don't do anything. So this is no distortion, but we don't do anything. So that's why the output SNR will be as the input SNR. This is without any filter. This is obvious. noise reduction factor. So the same way that we define noise reduction factor for time domain and single channel frequency domain and so on, the noise reduction factor, we can define narrowband noise reduction and broadband noise reduction factor. So the broadband noise reduction factor is the integral or the summation of the power of the noise in the reference sensor divided by the total power of noise at the output of the filter, which is the total power of the residual noise. This ratio, and we want to have it to be as large as possible. And also we can define for the narrowband for each frequency separately. See? So we have this. Desired signal reduction factor, so the broadband and narrowband. The broadband is the total power of the desired signal at the output, at the reference sensor. And this is the total power of the desired signal at the output of the filter. If we have the narrowband, so the narrowband is without the integral, so phi, the variance of x1, cancel out, and we have this. So you see, for MVDR, for example, what will be the desired signal reduction factor? The narrowband. What will be the narrowband? First, I'm talking about the narrowband. What will be the narrowband desired signal reduction factor for MVDR? 1, which means that there is no desired signal reduction factor. Of course, it should be 1, always. With MVDR, we have no distortion, so the desired signal reduction factor is 1. No reduction. And the broadband, if we put here 1, you see for each frequency, it's 1. So also, the broadband desired signal reduction factor is 1. We see from the formula or from the definition. But of course, for MVDR, we don't have any distortion. So it's expected. We just want to verify, okay? But as expected. And also for the noise reduction factor and the desired signal reduction factor, broadband definitions are not integral of the narrowband definitions, the counterparts. And this is the constraint or the requirement that we put for the MVDR. This is the constraint that this number, you see that this number will be constant 1 for all frequencies. So when we reach to distortionless constraint, this is the constraint for the MVDR or other filters that we have with the requirement of distortionless constraint. And we have similar relations like we had for the other domains, that the gain in SNR, either for the narrowband or for the broadband, it's the ratio between the noise reduction factor and the desired signal reduction factor. Let's define the desired signal distortion index. So what is the desired signal distortion index? It means what is the mean squared error of the difference between the desired signal. You see here, it equals to X filter desired plus V residual noise. So if we take the difference between this and X1, take this error and we normalize it, we get the distortion index. You see, so this looks like this. Here, let's see the narrowband first. So the narrowband, X filter desired minus X1, magnitude squared, expectation. So this is the variance of the error. The mean squared error of the distortion, normalized with the variance of X1. We obtain this expression. So this is the distortion index, the narrowband distortion index. if we compute the broadband desired signal distortion index, so we have the integral here, the integral of the error. We sum the error over all frequency. And also here we have the integral in the denominator. And actually you see that this is the number, so we get here, we get the distortion index is the integral of the narrowband distortion index. It's a weighted sum. It's a linear superposition of the distortion in each frequency of the narrowband. Based on the weight is the variance of x1. Okay? Of course, because if in each frequency we have distortion, so the total distortion will depend on the strength of the signal in each frequency. So if I have distortion index, it's normalized, okay? It's normalized. If I have some distortion in some components of the signal, like percentage, it's normalized between 0 and 1. And so 10% distortion in strong components is much more significant than 10% distortion in weak signal components. Okay? So the broadband distortion index is the summation of the narrowband distortion index multiplied with the variance of the signal. From this definition, you see it. But it makes also sense, because when you want to compute the normalized distortion index, it's normalized, yes? You give more weight to distortion where the signal is strong. That's why when you want to minimize the broadband distortion, you will try to minimize the broadband distortion by minimizing the narrowband distortion in the strong components. Because the strong components where the variance of x1 is large, it will induce much more distortion on the broadband, in the broadband. In the weak component, we can allow more distortion. That's why when we suppress noise, or when we want to control the trade-off between noise reduction and signal distortion, we allow distortion in the weak signal components. Because over there, the effect of broadband signal distortion is less significant in the weak signal components. Any questions? Okay. And of course, for MVDR, obviously, also the narrowband distortion is 0, and the broadband distortion is also 0. We don't have any distortion from this distortionless constraint. If we satisfy this distortionless constraint, we don't have distortion. No narrowband, no broadband. Using you see the definitions here. This will be 0. This will be 0, so the broadband also is 0. No distortion. Mean squared error. So mean squared error is the error between the estimate of x1 and x1. The mean squared error of this difference. So this difference is composed, if we take this difference, it's composed of, can be split into two components, which are uncorrelated. One component is the error between the filter desired and x1, so that it relates to the distortion. And the other component is related to the residual noise. So if we take the mean squared error, So we have that the mean squared error, we can find explicit expression of the mean squared error as a function of everything that we know and as a function of the filtering vector. By the way, when we compare multi-channel filtering in the frequency domain using this model, you see that we do it for each frequency independently. So the length of this, you see the length of this filter. What is the length? M, exactly. The number of sensors, which is much smaller than the length of the filter in the time domain for multi-channel. What was there? ML, okay? And even we worked with matrices, so the filtering matrix was L by ML if we try to estimate L samples at a time. But even if we try to estimate a single sample of the time domain signal at a time, we have a very long filter of length ML. And usually, L is quite large in the time domain compared to M. M, we use a few sensors. M is usually a few, maybe 2, 3, 10. Sometimes people use like 100 sensors. But usually it's around 10 sensors, up to 10 sensors, sometimes even less. But in the time domain, L is usually, can be very large, depending on the correlation between samples. What's happened? Okay. So this is the mean squared error. And then we can, because we have explicit expression as a function of the filter vector for each frequency, which here, it's nice, which is not too long. So it's easier to work with. And everything else is known. So we can find derivative of this narrowband MSC with regard to the filter, and then we can find the Wiener filter. And because we work on each frequency separately, it's much easier to derive, okay? We will see afterwards. But here, this is the narrowband MSC, and it can be written as the summation of two components. One is MSC that is related to the distortion, and one MSC which is related to the noise. And we can also define the broadband. Okay, so we have explicit expressions. And we can define the broadband MSC as the integral of the narrowband mean squared errors. Because it will give us the total mean squared error over all frequencies. You see that this relation that the broadband is integral of narrowband, it's only for the MSC. For the other performance measures, it's not. So don't confuse when you take broadband performance measure, it's not an integral or summation of all the performance measures in narrowband, in frequencies. It's not the total. Only for the MSC, it's like that. Even for the distortion index, it's not like that. It was a weighted sum. So generally, you need to verify if this relation. And why we are interested in the broadband? Because usually these are the performance measures that if we work with broadband signals, then we want to verify, we optimize the performance for the broadband performance measures. Okay? And we have different relations between both the narrowband and broadband performance measures. So even for the broadband performance measures, we have relation between the ratio between the MSC-based distortion and the MSC-based residual noise related to the other broadband measures, which is easy to verify. Now, after we defined the performance measures, we can move on to find optimal filters. So let's start with the maximum SNR. So maximum SNR, we wrote it somewhere before, but maybe it's not there anymore. Okay. So this is the output SNR for the MVDR. But generally, the output SNR, we saw that it looks like this here, this formula. Okay? So this is what we obtained here, which is the same. But it's nice to write it this way instead of magnitude squared. See? Why? Because here we have a matrix, and here we have a matrix. This is a scalar, a real number. And we have a ratio like this. So whenever we have a ratio of H and a matrix, let's call this matrix A, divided by H matrix B, of this ratio, okay? So whenever we have a something ratio like this, if we want to find maximum of this ratio over H, so we know the solution. The solution will be proportional to the first eigenvector of B minus 1A. So the first eigenvector of this, so H is proportional to this first eigenvector of this matrix. By the way, if you are not familiar with that, it's a nice exercise to prove it. Okay? By the way, if you're looking for also a nice proof, which is like a few lines of proof, it's in one of the textbooks of Van Tree. There is Optimum Array Signal Processing by Van Tree. It's a very thick book. So over there, there is also a few lines of the solution. Or you can check out in, maybe it's also in my book, in one of the problems. So there is also a proof of that. Okay, so we see that it's known that it's a maximized. So if we take this minus 1, see, minus 1, multiply with this matrix. So it will be the first eigenvector. But we know that this matrix is rank 1, okay? So if we take the maximum eigenvector, it means the eigenvector that corresponds to the eigenvalue, the largest eigenvalue of this matrix, then any proportional, any filter that is proportional to this eigenvector will generate the output SNR. So actually we can write it, if we take the largest eigenvalue, we denote it by lambda 1, the largest eigenvalue of this matrix. Okay, the largest eigenvalue of this matrix. We call it lambda 1. And of course, lambda 1 f. Everything is a function of f because we work for each f, for each frequency independently. So first we see that lambda 1 is can be formulated like this. How do we do it? Because lambda 1 is the trace of this matrix. How do we know that lambda 1 is the trace of this matrix? Okay? So this matrix, you see, the rank of this matrix is 1. So if we multiply rank 1 matrix with another matrix, we get rank 1 matrix. And you know, if the rank, the trace of any matrix is the summation of the eigenvalues. Okay? So if we have only one eigenvalue, the remaining eigenvalues are 0 because it's a rank 1 matrix. So the trace of this matrix equals to the eigenvalue because we have only one eigenvalue. So the trace of this matrix is the eigenvalue, the only eigenvalue that we have, which is the largest because we have only one eigenvalue. So how we compute this trace, and you know if you take two matrices, A, B, the trace of AB is the same as BA, the trace of BA. We can change the order. So the trace of this matrix, we can take gamma transpose and put it from the left. So we can change the order. So if we put gamma transpose from the left, we don't need to keep the trace anymore because this is a scalar. So we got an expression from of the eigenvalue. Okay, so it's very nice to see how we can find expression for the eigenvalue of that. So this is actually the eigenvalue. So this is the maximum that output SNR that can be achieved. So this is upper limit for the output SNR using any filter, or the output SNR that can be achieved using the filter that maximizes the output SNR. Using here things that we know. You see, we know these terms. And actually, what I want you to try to understand how this expression, how it relates to the maximum SNR that can be achieved. So when you get a mathematical expression, don't move on. Try to see what does it mean. Okay? So what does it mean, this expression? Because it's very nice to look at this expression. First, we see that it's proportional to variance of x1. Okay, nice. Nice that we have here variance of x1. By the way, we can take the correlation matrix of the noise and we can normalize it, so it will be variance of x1 divided by variance of v1. And here will be normalized correlation matrix. So of course the output SNR that can be achieved is proportional to the input SNR. It makes sense, right? Because the higher input SNR, the higher is the output SNR. It doesn't mean that the gain in SNR is higher. Usually, for higher input SNR, the gain in SNR will be probably smaller. Okay? But the output SNR is proportional to the input SNR, which makes sense. More input SNR, you have higher output SNR. So what I want you to look at this value, the value of this scalar. What does it mean? What does it mean? This vector, what is this vector? It's like the steering. We talked about overview of multi-channel. So it's just like steering. So this value says that when we steer the observed signal, so we look for signal, the desired signal, it comes from this direction, right? It comes from this direction. So when we look to the direction of the desired source, we see how much noise comes from that direction. You see, so this gives us the amount of noise that comes from looking to the desired source direction. So the output SNR, depends on two terms. One is the input SNR, because this we can normalize with the variance of V, so the input SNR. Second is how much noise comes from the direction when we steer it, when we look. So we steer it, the filter towards the desired direction. So this will give us the maximum amount of SNR. Okay? Questions? Okay, so I don't know if we have time. So we will continue. So actually, any filter that is proportional to this eigenvector, okay? So so we have also any proportion that we can take here, any numbers, but these numbers can depend on the frequency because we do it for each frequency separately. So any arbitrary numbers which are different than 0, we will get maximum SNR because it will generate the output SNR, which equals to lambda 1, the first eigenvector. Okay, so we will continue with optimal filters in the multi-channel. So if something is not clear yet, you want to work more closely, if you have time, follow the problems at the end of each chapter. Try to solve a few problems, try to see, so you get more intuition, more understanding of the material. And of course, you can always ask me different things, but you can also derive things by yourself, some of the steps that I showed here. So we will continue with optimal filters, and also we will talk about implementation with the STFT. So today we talked about multi-channel in the time domain. So I want you now go back for the single channel and the multi-channel. See the differences of the filter as how we define these things. Also, multi-channel in the frequency domain compared to the single channel. Okay? And each example, if you have time, each example that I show, they are MATLAB code. MATLAB codes for all the figures. So you can also play with that. You can take different examples. And